In this video, we're going to look at non-ideal gas behaviors. And essentially, a gas behavior when it is in a high pressure situation or a low temperature situation shows a different value other than one for this thing called a compressibility factor. And a compressibility factor is calculated by taking the molar volume of a gas at the temperature of that condition that gas happens to be in, taking into account the pressure and temperature of that gas, divided by the molar volume of the gas in ideal conditions at a temperature and pressure. And if that value is higher than 1 or lower than 1, then that gas is considered to be in non-ideal conditions. And so as you can see, this graph that you see here below is the compressibility factor on the right hand or left hand side is the y-axis, and the pressure on the x-axis. And as the pressure increases for gases, high pressures, the compressibility factor of those gases increases and increases as the pressure increases. And so it starts to not act in an ideal way. And there are two kind of factors or two ways in which non-ideal conditions affect gas behaviors. So the first one, high pressure, how that affects the gas behavior. And if you're taking a container of a gas, say this is a gas in ideal conditions here, and then we take the volume of that container and compress the volume down to about a volume that you see here. Well, what happens is if the pressure gets high enough and you're compressing that gas hard enough, what happens is the volume of the gas molecules themselves start to become appreciable, which meaning that say that this molecule here is trying to travel through the container. These molecules over here, all the rest of the molecules in the container, are starting to take up space that this now molecule can't get to, that means that now the volume of the container is no longer the volume of the container. You're starting to have things take up that space that other molecules can't get into. And so we have to do something about the volume that occurs with the molecule itself and have to put that into our calculations. And I'll show you how to do that in a bit. The second thing that we look at is what happens to molecules when we're at pretty low temperatures. And keep in mind, you guys remember that kinetic energy is directly proportional to temperature. And as the temperature gets really low, our kinetic energy or energy of motion starts to slow down. And so if you're at really high temperatures, you're moving along, trucking along, these molecules are moving along so fast that their attractive and repulsive forces have no effect on each other. However, if you have molecules moving really slow right by one another, what happens is they start to have attractive forces pull those molecules in towards one another. Now, when that happens, you start to affect the trajectory of those molecules to a point where now they're not going to hit the inside wall of containers at the original force that they would have previously. And essentially what that does is that decreases the pressure and can decrease the effect of the volume slightly by that attractive force, because your kinetic energy cannot overcome that attractive force at these super low temperatures. And so we have to correct for this as well, that attractive force. So we're going to do this using an equation called the van der Waals equation. Sometimes you might even see this written or known as what we call the non-ideal gas law. And we're going to use two correction factors, one for the volume of the gas molecules themselves and one for the attractive forces of the molecules between each other. Now, we're going to start with the ideal gas law, and we're going to add these correction factors in. And the way that they work is, for our pressure, how we're going to correct that is using a correction factor that's written as A times N squared divided by V squared. And the A is a kind of a value that takes into account the strength of the attraction of those molecules to one another. And the volume will get corrected by a correction factor that is N times B, where B is the size of the gas molecule itself, so it's taking into account the size of the molecule and correcting the overall volume of the container by taking that into account. And so this right here is considered the van der Waals equation, or the non-ideal gas law. And this particular guy is what we'll use to start calculating things, or calculating non-ideal gas behaviors or values about gases in those non-ideal conditions. Now, I wanted to give you the kind of some of the values of these common constants for A and B, these correction factors. And there's a table in your text that has a few gases, but you can look these up in the back of your textbook or just Google them online. But here are a few for you. The correction factor A for a couple of gases is here, but the units are pretty important to keep in mind. For A, they're L squared, or liters squared ATM divided by moles squared. And the units for the B correction factor is liters per mole. And so let's go ahead and try to calculate some non-ideal conditions on a particular gas. So this problem says you have a 0.245 liter flask that contains 0.467 moles of carbon dioxide. So this is our gas in question. And we know how much of it we have, and we know the volume of the container that is containing that gas. And it turns out we're at a temperature of 159 degrees Celsius. And it says, calculate the pressure, okay, so this is P, in non-ideal conditions. So we're assuming, I'm telling you, that this gas is non-ideal conditions, and any problem that I require you to use the van der Waals equation or non-ideal gas law, I'm going to tell you to do so by saying this. And so we're going to use that equation of P plus AN squared divided by V squared times V minus NB equals nRT. And so a couple of things we need to do housekeeping wise is we need to determine what A and B are for CO2. And if we go and look those up in the table, we have 3.59 and 0.0427 with their respective units. And so let's make sure that we have those written down of liters squared ATM per mole squared. And for B, that is 0.0427 liters per mole. So let's have those. Let's make sure that we have our V, that's 0.245 liters. We have our mole value is, or N rather, let's use the appropriate unit or variable, is 0.467 moles. Our temperature we do have 159 degrees C, but remember we have to put that in Kelvin. That ends up being 432 Kelvin. We know an R. Let's go ahead and kind of look at kind of the things. What R are we going to use? Are we going to use 1 kilopascals or ATM? Well, it turns out that our A correction factor has ATMs in it. So let's just use the one with the ATM. So 0.08206 liters ATM per mole Kelvin. All right, so I think we have all of the variables we will need. It's just a matter of plug in and solve the problem. So I will say that plugging all of these numbers in with the units into this particular equation takes quite a bit of space. So I suggest you start as far as over to the left as you can. And how do you know what we're solving for? What's the pressure? So that P value here, that's what we're solving for. So we're going to plug everything in, and I want you to see what this looks like. So P plus A, which is our 3.59 ATM, liters squared ATM per mole squared. And that's going to be times our moles squared. So our N squared, 0.467 squared mole squared. So keep in mind whenever you square something, make sure you square the number and the unit as well. And then we're going to divide that by the volume squared. So 0.245 squared liters squared. Okay, now the volume again, 0.245 liters minus the mole, 0.467. And I'm going to put this in parentheses and multiply that times our B correction factor of 0.0427 liters per mole. And put that. And then we're going to have our nRT, so our N is 0.467 moles times our R is 0.08206 liters ATM per mole Kelvin times our temperature of 432 Kelvin. Okay, and so this problem it's a lot of fractions and squaring and parentheses, and I highly recommend you go through and do like sections at a time. So what I would do is do all of the math in this parentheses, and then do all of the math on this side, and then do all of the math here. And then what you'll end up doing is having your pressure be equal to all of that stuff moved over to the right-hand side. And if you need some help kind of doing this basic algebra, enter a comment, send me an email, and I can post another video on that. But what I'm going to do is I'm going to go ahead and give you the answer. And this ends up being 60.8 ATMs. And so this particular value would be the pressure of that gas in non-ideal conditions. You could go through and use these exact same values and figure out what the pressure would be in ideal conditions. You just wouldn't use this equation. You would use the normal ideal gas law. So this has been a video to show you how to calculate the pressure at non-ideal conditions using the van der Waals equation.